Can you hear me? Oh yeah, okay. Hi everyone. So welcome. It's wonderful to see so many of you today, and I hope you'll have a great week. So I have a few practical announcements for this opening remarks. So it's really going to be very concrete and not in any particular order. Okay, so first I want to recall the code of conduct and the fact that we are here to have an experience which is free of harassment and discrimination, that respects the dignity of every participant. So if you notice anything or if you are like a victim of anything, you can reach out. In particular, Adeline and Katarina, whose photos are on the slides, as main contact points, and here is a list of other contact points, which is also, so all this is also on the webpage. Food. For lunches, so there is a variety of options, including meat, fish, vegetarian. Those who have stricter diets, like me, have coupons for specific lunch trays. So that should be in your badges. So inside the 2 sheets of paper, if you have a stricter diet, you should have coupons inside your badge. And these you can use to exchange for your specific lunch tray at lunchtime. For the banquet on Wednesday evening, there is yet another coupon. So everyone has one. It's describing your menu for the waiters and waitresses at the banquet. And please place it very visibly near your plate before being served, because it's helping to go faster with serving dishes. A very important message. So you've already seen that we are quite a lot. We are reaching catering capacity. So the lunch place or in the banquet place, it's 715 seats, and we are 715 registered. So when you go for lunch or banquet, please fill every seat from the back of the room. Otherwise, it's going to be complex. Short message to the speakers, session chairs, and authors. So speakers, please upload your slides at least 24 hours before your talk. So we are still missing slides for today. So yeah, please hurry up. Find your session chair before the last break preceding your talk. Session chairs, check the speaker's name, speakers' names of your session. Arrive a few minutes before just to see if everything works, and make sure the speakers stay on time. So yeah, please respect the times very carefully. And a last message for authors. So in principle, all papers accepted should be on e-print, but the principle is not practiced at this stage. So those who have not uploaded on e-print, please do. RAM session. So the chairs this year are going to be Alison Bishop and Or Dunkelman. The deadline to submit your talk is on Tuesday at 1 p.m. So the RAM session is on Tuesday evening. Talk duration 1 to 5 minutes, and 6 in very special circumstances. And you can submit on so the submission website is a page of the Eurocrypt webpage. Okay, so more info. If you need help, the volunteers can be recognized by red lanyards, so the necklaces. You can also find help at the registration desk. There will always be someone during the week. Badges. Please wear your badge at all times. And if you haven't understood the previous slides, no badge means no food, because your coupons are in your badge. If you lose your badge, please come to the registration desk. A few days ago, we added the tourism page on the Eurocrypt white page. So if you need tourism IDs, there are a few there. Also for restaurants, there is no dinner provided by the conference tonight. Monday evening is not the easiest to find open restaurants in France. So there is a list of restaurants that we check are open, and this list is also on this webpage. When you leave, if you don't want to keep your badge as a souvenir, you can give it back and we'll recycle. And also when you leave, you can get your farewell gift. So there was no gift at reception today, but there is a gift when you leave. Okay, so I think that's it for now. I just want to thank all the sponsors that helped to significantly decrease registration fees for everyone. So thanks to the sponsors. And now I leave the floor to Kermit.
Okay, good morning. Is it working? Yeah, you can hear me. Okay, good morning and welcome to our first invited speaker session. We are delighted to have Guy Rothblum here. Guy completed his PhD at MIT and was a postdoc researcher at Princeton University. He has been a visiting researcher at Stanford University and a researcher at Microsoft Research, Silicon Valley Lab, and Samsung Research. And he's currently a researcher at Apple and an associate professor at the Weizmann Institute of Science. He received the 2018 Maurice Levinson Prize in Mathematics and the 2020 Blavatnik Award for Young Scientists in Israel in Physical Science and Engineering. Guy is a versatile researcher, and his research focuses on multiple areas, such as cryptography, complexity theory, and social concerns in algorithm and data analysis. He has fundamental results in proof systems, obfuscation, and privacy. Let me just give you two examples. Designing interactive proof system with sustained verification is a problem of efficiently verifying the results of outsourced computation on an untrusted remote computer. Guy's work on interactive proofs for muggles, along with Shafi Goldwasser and Yael Kalai, is an influential work that in the past decade has become the basis of designing concretely efficient snarks, which are instrumental in bridging efficiency and privacy in blockchains. Guy also made influential contributions in the field of privacy and differential privacy. His work with Moritz Hart on multiplicative weights mechanism remains a significant approach to dealing with a large number of statistical queries. Besides these, Guy had made important contributions to learning, obfuscation, fairness, and realizing the future heuristic. And he's a fantastic speaker. In this talk, he will discuss indistinguishable predictions and multi-group fair learning. So without further ado, let's welcome Guy.
Thank you, and thanks, Kermit, for that lovely introduction. And now there's nothing left to do but disappoint you after such an introduction. Okay, so I wanted to speak about work that I've been doing with some collaborators in recent years about fairness in machine learning and automated prediction, and also thinking about the meaning of predicting individual probabilities in machine learning systems. We'll talk about it. And one thing I want to get across right from the beginning is that we've taken a very cryptographic or cryptographically inspired approach to these problems. And these are really important problems. So I hope, if you see something you like, or if you see something you don't like, that you will also join the research effort thinking about these questions. And I should say, because Apple asked me to say, that this is mostly work that I did before joining Apple. Okay. So predictive algorithms, we know, are everywhere, and they're only becoming more and more prevalent in society and more influential. I really love this New Yorker cartoon. Can you see the pointer or not so much? Okay. Yeah, so I love this New Yorker cartoon. Algorithms are determining who are influencing who we meet for our life partners. Of course, they're also influencing decisions that are made about us in medicine, in the finance system, every time you apply for a loan, for example, in criminal justice, if you ever need to come up in the US criminal justice system up against a judge, there's a good chance that an algorithm will be advising or helping that judge make a decision about you. So really, these are hugely consequential decisions being made about individuals at scales that we couldn't really conceive of, I think, even in the recent past, and it's only going to get more so in the future. And there are many advantages to automated prediction. For example, if they can make a better medical diagnosis than a doctor, or do that at a scale that a human doctor cannot do, that can be tremendously beneficial. But there are also very serious concerns. And a prominent concern is fairness of the predictions. It's not the only concern that I'll talk about today, but it's a prominent concern. And I pulled up some headlines yesterday when I was preparing when I was finishing the slides. Some horror stories, and really what seems to get the most press is when there are discrimination issues with algorithmic predictions. So these are some examples from the world of hiring, from medical risk prediction, and for the criminal justice system in the United States. There's some excellent literature that I really recommend you check out recently, algorithms of oppression or weapons of math destruction, really good literature detailing these types of concerns. So that's what I want to talk about today, and I think the challenge for us as computer scientists and as cryptographers is, can we come up with a principled, reasoned, mathematical way of thinking about these kinds of problems and concerns, and can we find a way to handle them, to mitigate them, to get the benefits of machine learning without some of the really devastating harms? Okay, so I want to start right off by saying that I'm going to talk about prediction, but no one really knows what they're talking about when they talk about prediction. When we have a predictor, usually they're called risk predictors, they try to assign a number between 0 and 1 to an individual instance. Okay, maybe we have some measurements about the climate and we want to predict the probability it will rain tomorrow. So the algorithm spits out a number between 0 and 1. The number is understood as a probability, but that's a problematic interpretation, as we'll see. Another example, we have a loan applicant with certain features X. What's the probability that they will repay the loan that they're applying for? Given some medical imaging, what's the probability that this tumor, whose imaging we're looking at, will metastasize? What's the probability that a defendant with a certain set of features Y will commit a violent crime if we release them on bail? Okay, so these are important questions. We would love to know these probabilities. I think that could be really world-altering if we could. But notice that all of these events are non-repeatable. The tumor will metastasize or it won't, right? The loan applicant will either repay the loan or they won't. The defendant will commit a violent crime or they won't. We don't get to rerun the experiment. We just get to see an outcome, 0 or 1. So, maybe I got a probability of 0.8 of repaying the loan, then I did or I didn't. What's the probability over? What do these probabilities we're trying to get at mean? And that's a deep question that has sort of been handled by statistics and the forecast testing literature for decades, and we're not going to answer it today, but I think by the end of the talk, hopefully, we'll get a very cryptographic new perspective or a new approach to thinking about the meaning of these individual probabilities. Now, the probabilities are particularly problematic because of concerns like fairness, so I want to say a little bit about fairness before we delve into things. So these algorithms are not operating in a vacuum. They are operating on people, on individuals with a certain context and a certain society behind them. And the population includes minorities that are protected either by law, by ethics, by policy. Fairness is important, and it's not a new concern. Fairness, the study of fairness in various contexts has been going on for millennia, spanning many disciplines. But the types of problems we are being tasked with now are new, and they come from computer science, and I think you can't really reason about them without taking a computer science perspective. So computer science is part of the problem, and it also has to be a part of the solution, and there's a whole field now of algorithmic fairness that tries to reason about the fairness of decisions or predictions being made by algorithms, with the hope that algorithms can make equitable decisions. But I just want to say, and I have to say it, although I think at this point, hopefully it's obvious to everyone, if you just train a machine learning algorithm on data drawn from society and ask it to make predictions, it is not going to be fair on its own. Okay, it's going to be biased because the data are biased, because it's trying to optimize for the general population, not for minorities, because sometimes it's trained with the wrong objective. So we really need to think about these things deeply. And ideally, what we would want, again, thinking about this as a cryptographer, well, I would want a mathematical definition of fairness, similar to the way we have a definition of semantic security for encryption, and we have stronger definitions, and we have a definition like differential privacy for privacy-preserving data analysis. And I would similarly want to write an equation telling you mathematically, here is what fairness in the world means, and then we would make sure that all the algorithms we use satisfy the equation, and we would be happy. I think that's a good hope. Unfortunately, fairness seems to be a lot trickier than things I've worked on, like encryption or privacy-preserving data analysis. Fairness is very context-dependent. So, for example, targeting women and men differently if you're advertising a shampoo is usually not problematic. Whereas if you're targeting men and women differently in a hiring ad for a job, that's illegal in many countries. Okay? So it's very dependent on context and societal norms. It's very subtle. Actually, even just auditing, understanding whether what's going on in a system is fair or not, let alone devising a fair system, can be very problematic. But I've decided to not be depressed about this, but rather to be happy about this. And thinking about this as cryptographers, I think it's a huge opportunity. And the opportunity is, we're not going to get away with finding just one definition, but we have the delightful, or I don't want to say delightful because some of the things you encounter when you work on fairness are really troubling, but we have the exciting job of understanding what the threats are, cataloging, concerns, and coming up with countermeasures for particular contexts that are of interest. And we'll have a whole family of, hopefully, of definitions and algorithms and countermeasures and techniques. And I think that's the goal, at least for the theoretical study of algorithmic fairness. Okay, so that's a backdrop for what I want to tell you about today. I want to talk about how to make predictions meaningful. Okay, so what does it mean when we're predicting an individual probability, and how can we think about it? And we have a new framework, very much inspired by cryptography, that we call outcome indistinguishability, a new criterion, definition, desiderata for prediction that will help us to understand, to think about predicting one-shot events. And we'll see that I think it's interesting in its own right, and it's also going to be very helpful for achieving fairness and strong notions of fairness. And hopefully I'll have time to tell you about both of those today. Okay, so let's start off with our setting, these individual probabilities. We've said it's very problematic. We predict a probability of 0.7 of rain. Either it will rain or not. We don't get to observe the underlying true probability of rain according to nature, or similar for loan defendants or for loan applicants or criminal defendants. In fact, we don't even know, this is a philosophical question, right? Does uncertainty even exist? I mean, what is 0.7? Maybe, if I knew the state of all the particles in the universe and I had a sufficiently strong computing device, I could just compute everything. Is it going to rain? Is this defendant going to commit a violent crime? Are there probabilities? What is this 0.7 trying to capture? I think colloquially it's trying to capture, okay, given what we know and given sort of similar instances, what should we expect to happen? But that's a very loosey-goosey sort of definition. So let's try to make it a little more precise. So what I want to think about throughout the talk today is what's known in machine learning as the batch setting. So we have an underlying distribution. Usually we call that nature. I can't see my pointer, but maybe you can. We call that nature, and we get to see observations. Every observation is a set of features, X, maybe the features of a loan applicant, and an outcome, Y. I usually call it Y star. The star indicates that this is nature, this is being governed by reality. Y star of X, and we get to see a Boolean outcome. Did the person repay the loan or not? And I'm assuming that the distribution for the talk today, the distribution is static, and we are seeing examples drawn from it. We don't get to see the same person twice, but the distribution nonetheless is the same, is fixed. And now, once we have this distribution in mind, we can define what we mean when we say individual probability. What I really want is the probability for this particular person with this set of features X. What is the probability of the outcome being 1 under the distribution D? Right, that is the correct individual probability, which I'll call P star of X in the talk today. So for example, maybe nature or P star, we have all these green people, and each of them has a probability of exactly 0.5, a fair coin toss of being a 0, having an outcome 0 or an outcome 1. And when we start drawing examples, we start observing reality, we see some of these people get an outcome of 1, some of them get an outcome of 0. Okay, and I'm gonna say it a million times in the talk today, but I'm gonna say it a million times because it's important. We only get to observe the outcomes. What the true probability of an individual is unknowable, and we might have deep philosophical disagreements about what it is, or whether there is randomness, whether everything we should be thinking of as deterministic. We only get to observe the outcomes. We don't know what P star itself is. Okay. And that raises this problem, which I've been hinting at. We've taken to calling it the unresolvability problem. Do probabilities exist? Do they not exist? Suppose I tell you that I think P star, really the true probabilities governing reality, are 0.5 for everyone. Now there are two indistinguishable worlds. Maybe it's 0.5 for everyone, or maybe it's 1 for say a random subset of the individuals. Maybe there's some feature we don't have that would tell us who the ones are and who the zeros are, but as far as we see now, there's a random subset of the people who are 1 and a random subset of the people who are 0 according to P star. There's no probability, and we're just seeing deterministic outcomes. We can't tell. These are two indistinguishable realities. So when I tell you that a probability is 0.5 or 0.7, what does that mean? How can we reason about how good or accurate these probabilities are if we can never agree on whether things are probabilistic or deterministic in the first place? Okay, so of course I didn't invent this problem. This is a problem that machine learning people and statisticians have been dealing with for decades. So what are some approaches for evaluating predictions, probabilistic predictions? So the prevalent approach in machine learning is what's known as loss minimization. We define some loss function that tells us how close these predictions are to the outcomes. Maybe the squared loss, the difference between the predicted probability and the outcome that we see, squared, or you could take the absolute value, but some function that is hopefully shrinking as the predictions are getting more accurate, and we try to minimize the loss. Okay. So, of course, there's the question, what is a good loss? Now, suppose I tell you that the loss of the predictor is 0.3 on average. Is it good? Is it bad? If everyone is a balanced coin toss, and I give you a loss of something like 0.25 in square loss, the perfect predictor will actually have significant loss. Okay, if there's a lot of randomness in the system, even a perfect predictor will have significant loss, and that's okay. There's randomness in the system. We don't think we can do better than that. So the smaller the loss, the better, but in many complex prediction tasks, predicting whether a defendant will commit a crime, predicting whether a loan applicant will repay the loan, there is uncertainty as far as we can tell, and there will be loss. And now the question of what is a good predictor, I don't know what a good loss is for this particular task. Moreover, the loss is global, it's an aggregate. So maybe the predictor is doing really, really well on the general population, but doing poorly on a minority. We see that all the time. So loss minimization on its own doesn't really tell us whether the predictions are meaningful. It does give us a way of ranking predictors, right? Like this predictor has less loss than that predictor, so maybe we like it better, but it doesn't tell us on its own whether a predictor is good or what it means. The standard approach, at least in the theory of machine learning and agnostic learning, is to show that the loss is competitive. The loss you're getting is, at least is better than or not worse than the best decision tree or the best neural net of a certain size or the best regression. Still, is that good or is it not good is a very subjective question. Okay, the other approach taken from the forecast testing literature, which also plays a role in modern machine learning, is what's known as calibration. So these are sort of sanity checks for the predictor. For example, if the predictor is predicting 0.7 for a certain collection of days, right, or a certain collection of individuals, then if for 70% of the instances on which the predictor predicted 0.7, the outcome should be 1. Certainly, if the predictor is giving us the correct probabilities, this should be the case. Right, when it's predicting 0.7, 70% of the time we should be seeing a 1, but calibration on its own is pretty weak, right? Suppose, for example, that it rains. We know that in Lyon it rains 30% of the days. I don't know if that's accurate or not, but I can just predict 0.3 for every single day of the year in Lyon, and 30% of the time it will rain, 70% it won't rain, more or less, and my predictor is calibrated, but the predictions are not very meaningful or informative. Right, so calibration is a good criterion, but it can be achieved, especially in the batch setting, sort of easily. And again, it tells us if a predictor is not calibrated, then we know something bad is going on. If I look at the places where the predictor predicted 0.7 and I see that they were never 1, it was always zeros, then something is wrong with the predictor. So if there's no calibration, there's a problem, but calibration on its own doesn't really tell us how to, if the predictions are meaningful. And so given a predictor, and I should have said it, the predictor throughout the talk today is going to be P tilde. So P star is the truth, the true probabilities. P tilde is some predictor that's being given to us, and we want to evaluate it. And how should we evaluate it? So I want to go back to this sort of unresolvability question and think about it from a cryptographic perspective. So suppose we see these observations and we see in nature that we have 1s and 0s. But I tell you now that the 0s and the 1s are completely indistinguishable, either because we don't have the right features or because they're pseudo-random or because of our computational constraints. There's just no way we can distinguish the collection of people who have outcome 0 from the collection of people who have outcome 1. And it's about 50-50. 50% of the people get a 0, 50% get a 1. Okay? So now we're in a situation where if we hypothesize that nature gives everyone a 0.5, this hypothesis is indistinguishable from the reality. And for us, I think as cryptographers, we're pretty comfortable with this kind of situation, and in fact, that's going to be our goal. When we talk about outcome indistinguishability, we want to come up with predictions that are indistinguishable, computationally indistinguishable, from the reality, from the real outcomes that we'll see. Okay. So this is a slide I really like from Avi Vigderson. When we talk about randomness, randomness is in the eye of the beholder. When we toss a coin, we say that if it's a fair coin, there's a probability a half of it coming up heads and a half of coming up tails. In reality, it might be the case that when we toss the same coin, if we pointed, 1,000 different cameras at it and ran a bunch of supercomputers, while the coin was in the air, we could determine whether it's going to be a heads or a tails, whether it's going to come up heads or tails, whether the outcome is going to be 0 or 1. So really, it's a question of information and computation power. And we're very comfortable with this. And assuming that we don't have 1,000 cameras to point at the coin and a supercomputer to devote to this, giving a prediction of a half is indistinguishable from the reality that we're going to see, and that's a pretty good prediction. Okay, so I do want to make a brief detour, even though for this audience, I think computational indistinguishability should be something you're familiar with. Still, this is something that's coming from the world of cryptography and complexity theory, and when we talk about indistinguishable distributions, we mean distributions that, say a pseudo-random distribution looks uniform, or distributions that look like each other, even though in reality, if you look at the L1 distance, the statistical distance between them, they could be far apart. So two distributions, we say D0 and D1, are computationally indistinguishable if for a large class of distinguishers, usually we think about every polynomial time, every feasible distinguisher that we can run. If we feed a sample from D0 into the distinguisher, or a sample from D1 into the distinguisher, the distinguisher outputs 0 or 1, and it would output 1 with approximately the same probability. For every distinguisher, so any procedure, say, that you can run in polynomial time, will output 1 with the same probability on these two distributions, and we say they're indistinguishable, and as far as we care, in many situations in cryptography, the distributions are interchangeable. We don't care about which one we use. No one will ever be able to tell the difference between them. So with that in mind, I want something similar for a predictor. I want predictions that are indistinguishable from reality, and then I will be happy. Okay? So I'm thinking now about a predictor that we're being presented with, p tilde, as a generative model, right? P tilde is telling us how the outcomes for every possible x. P tilde of x is going to tell us, is essentially giving us a model. It's positing that the outcome, the Boolean outcome for x, is going to be drawn from a Bernoulli distribution with probability p tilde of x. And we can talk here about two realities. Maybe the reality is as p tilde predicted, so it predicted 0.5 for everyone, and we have the reality on the left in green. Or maybe it's predicting 0.5 for everyone, but the reality is on the right. There's a random set of zeros and a random set of ones, a random subset of zeros and a random subset of ones. And I want, if the predictor being outcome indistinguishable means that no distinguisher in a rich class can distinguish these two situations. So outcomes drawn according to the predictor and outcomes drawn according to reality are indistinguishable distributions to every distinguisher in a very rich class. Say for now, you can think about any polynomial time distinguisher. Okay. So to make it a little bit more concrete, let y tilde be the predicted outcome distribution. Okay, so y tilde is outcomes drawn according to p tilde. P tilde is saying 0.5 to everyone, so y tilde is a balanced coin. The distinguisher is either going to be presented with the features x and the prediction p tilde and an outcome drawn according to p tilde, 50-50, 0 or 1, or it's going to be presented with the features x, the prediction, which is 0.5, and the real world outcome. And the distinguisher cannot tell which is which. Okay, that's going to be the requirement of outcome indistinguishability, or OI. Okay, so I want that for every distinguisher in a very rich class, the probability that it outputs 1 when the outcomes are drawn according to the predictor. So this is a definition for the predictor. P tilde satisfies the definition. If for every distinguisher, the probability that it outputs 1 on outcomes drawn according to p tilde is the same as the probability that it outputs 1 on outcomes drawn according to reality, according to p star. Notice that p star itself does not appear here. We are not saying that p tilde, the actual probability predicted 0.5, is indistinguishable from the true probability p star. And it's for good reason. First, that would be a hard definition to achieve. And second, no one ever gets to see p star, right? We don't get to see what the true correct probabilities are. We just see outcomes. And two things to emphasize: the definition includes a class of distinguishers. So ideally, we'd be thinking about any feasible computation, any polynomial time computation. But we could be thinking about more restricted classes of distinguishers as well. And there's also a particular representation being fixed, the features x. So maybe, if we had some extra feature that we don't have at the moment, we could distinguish whether everyone is a 0.5 or there's a set of zeros that we can distinguish from a set of ones. So the features are also, the information we have at hand is also important. Okay, so that's the definition of outcome indistinguishability. Very, I think, hopefully as promised, very sort of cryptographically inspired or cryptographic in flavor. And I think it has a very nice, it's a very nice, nice semantics or a nice type of guarantee. So the way we really think of it, this p tilde, this predictor that we're being given, is really a model for how the world works. It's telling us how people are going to repay their loans. Or alternatively, if you're thinking scientifically, you could think of it as a theory, a scientific theory for how the world operates. And assuming we have a very rich class of distinguishers, outcome indistinguishability guarantees that the behaviors that the theory predicts, okay, so the way the theory predicts that people will repay their loans, and the actual behaviors observed in the real world are completely indistinguishable. Okay? No one can tell them apart, and in particular, no one can refute this theory. There is no way to falsify the theory, right? If you want to falsify it and say, no, you predicted, your model P tilde predicted 0.7 for this collection of people, but actually I'm saying that they only get a 1 with probability 0.2. Well, that's a distinguisher. So if there are no distinguishers, there's also no way to falsify the model or refute it. Of course, that's with this collection of distinguishers that are doing the refuting, and with this collection of features or information, with this representation of individuals. If we get a richer representation, if we collect more features, more data, maybe we can falsify the prediction, the predictor or the model. But one thing that's nice about our results is that this is actually, if you do this, this is a path towards progress. So if you do collect more information and you're able to find a distinguisher, you can use that to update the predictor, get a new indistinguishable predictor, and this is a path towards progress in the sense that your predictor is only getting closer and closer and closer to the true probabilities P star. So once we think about prediction as a goal of, once we think about the task of prediction as a goal of generating sort of an indistinguishable model of how reality works, it brings up an interesting hierarchy of definitions or of strengths in terms of what kind of access does the distinguisher get to the model, to the predictions. So I focused on what we call sample access indistinguishability, where the distinguisher gets the probability predicted for a particular instance and an outcome that is drawn either according to the prediction or according to reality. But you could give less access. For example, don't give the predictions, only the outcomes, and you could give more. So you could give the distinguisher black box access to the predictor, you could give it code access to the actual code of the predictor, and this makes a difference. Of course, the more access you give to the distinguisher, the more powerful the distinguisher gets, the harder it gets to create an indistinguishable predictor, and the stronger the guarantee. You could also talk about giving the distinguisher more samples. And I don't want to talk about hybrid arguments. Okay, so I don't want to tell you too much about algorithms. I won't tell you too much about algorithms. I just want to tell you that this is a really strong definition, and you might worry that it's too strong, but actually we show that it can be achieved. And we show this through a connection to a notion of multi-calibration. I didn't say. So this work on outcome indistinguishability is joint work with Dwork, Kim, Reingold, and Yona. And we show an algorithm for getting outcome indistinguishable predictions. This goes through reduction to multi-calibration, which is from a work with Herbert Johnson, Kim, and Reingold. Doesn't really matter how the algorithm works. What I want to tell you is that for any class of distinguishers that you give me, there is a procedure that can learn an indistinguishable predictor using a logarithmic number of samples. So logarithmic in the size of the class that you're specifying. So if, for example, you want to be indistinguishable to all circuits of size n to the 4, you can do that using a polynomial number of samples. Either an exponential number of such circuits, and you can learn an indistinguishable predictor using only a polynomial number of examples, where by examples I mean samples drawn from the distribution where you only get to see outcomes. You never get to see P star, you only see outcomes. Did the person repay the loan or not? And you can come up with an indistinguishable predictor, P tilde. This is an information theoretic result. There are serious computational issues. So the algorithm, if you ran it naively, would require exponential running time, the learning algorithm. And this is for similar reasons to the fact that many machine learning algorithms, if you look at the running time that you need for many machine learning tasks, it should be exponential. In reality, we can do agnostic learning, or machine learning works better in practice. And in fact, these algorithms have been implemented and they run pretty efficiently for many interesting tasks. Now, I think there are two sides to the coin. Is it good news that we can get indistinguishable predictors? On the one hand, it's great, right? If we're doing machine learning, we can have predictions that no one can falsify. Hopefully these predictions are not doing anything that doesn't make sense, right? They're indistinguishable from reality, so there's no way to find that the predictor is doing something really silly. On the other hand, there's no guarantee that these predictions are actually close to the true P star. right? It could be that we're predicting 0.5 for everyone, P star is 0 for half the people and 1 for half the people. So our predictor is very far from reality, but it's still indistinguishable. So I haven't solved, and I can't solve the question of ensuring that the predictions are close to P star, if that's what you mean by meaningful. Nonetheless, I think that this notion of indistinguishability is good news, and the guarantee we're getting is quite meaningful. Okay, I told you that there were stronger levels of indistinguishability. In particular, you could give the distinguisher oracle access to the predictor, so it doesn't only see the prediction for the particular X that we have at hand, but it can ask about other related individuals and see what the predictor does. We can still get outcome indistinguishability, even when the distinguishers have oracle access or code access to the predictor. Things get a little more hairy. The sample complexity becomes exponential in the error that you want to achieve, in the indistinguishability error that you want to achieve. And this is inherent. So we also have matching lower bounds. So it really is harder to get indistinguishable predictors if you allow the auditor or the distinguisher to have oracle access or code access to the predictor. And we view this as an argument for actually, if we're using, for example, algorithmic predictions in the criminal justice system, okay, to decide on bail conditions, we really should be giving the auditors oracle access to the algorithm making the recommendations about bail, or even we should be giving them the code so they can audit it. And such auditors really are more powerful, at least from a theoretical perspective. Okay, so that's all I wanted to say today about indistinguishability of predictions, and now I want to move things back to fairness and explain how this is related to fairness, and in fact show that once we have indistinguishable predictions, we can get really strong notions of fairness for the predictions that we're making. So just before we start defining fairness, what do people usually do? When we talk about a predictor and we want to ensure the predictor is fair or is not being discriminatory, in practice, the overwhelmingly most common approach is we define a protected set that we're interested in, say a racial minority, maybe a few protected sets, and we try to ensure some sort of equal behavior of the predictor on the general population and on the protected set. Okay, so to avoid a situation where, for example, our facial recognition software works really well on white people, but works poorly on darker-skinned people. It's a famous example of a behavior that's been demonstrated time and again, and something that people are concerned about. So that's known as group fairness. We're just thinking about two groups or a small number of groups in aggregate, and we want to equalize the behavior of the predictor across the two groups. And when we say equalize the behavior, there are various interpretations of what that means to force the predictor to behave similarly. So one notion, which sometimes is appropriate and sometimes is not, is to try to guarantee statistical parity. Okay, so say the average predictions or the distribution of predictions for the general population and for protected group S are similar. Okay, now of course it could be that in a certain minority, the probability of repaying a loan is higher or lower than the general population, and then statistical parity wouldn't be appropriate. Often this is sort of a corrective. It doesn't necessarily go in line with the data, and we apply it as some sort of a corrective transformation on the predictions. But there are also many things that we try to do that are in line with the data, and especially trying to ensure similar accuracy or similar types of errors on the general population and on the protected group that we have in mind. And these are in line with the data, so maybe we try to equalize the false positive and false negative rates, or we try to ensure calibration so that the predictor is not just globally calibrated, but in fact it's also giving calibrated predictions on the minority group, or even loss minimization. So make sure that the predictions, once we restrict to the minority group, the predictions that we're getting are still, have small loss, small error, and are competitive with the best, say, decision tree or the best neural net of a certain size. Okay, so there are various interpretations. All of these, I think, are quite weak, and I'll give an example on the next slide. They're also at odds with each other. So for example, you cannot both have calibration on S and on T and equalize the false positive and false negative rates, except under degenerate cases. But in all the interesting cases, you have to choose. Either you're getting calibration or you're equalizing the false positive and false negative rates. And I think, so, okay, that's a serious problem. But I think a fundamental issue here is that what is the group S we're talking about? If all we're doing, and this has to do with the weakness of these group definitions, if all we're doing is guaranteeing calibration globally over the entire group, or guaranteeing one of these behaviors globally over the entire group, we are often missing the really interesting stuff, which is what's happening in important subgroups. So here's the example that, I guess I've been waiting my whole life to give this example to an audience of cryptographers, because sometimes when you give the example, people think that it's too malicious or too adversarial, but this is not for this audience. So think about trying to enforce some sort of purity. So we have a steakhouse, a racist steakhouse, that is running an advertising campaign, and the steakhouse owner does not want any minority people coming to the steakhouse. Nonetheless, we're living in a fantasy land where everything is well regulated, and there is a regulation saying that you have to advertise at equal rates to the general population and to the protected minority. Okay, so what is an adversarial, racist steakhouse owner to do? You advertise to meat eaters in the general population, say 5% of them, that's your budgeting ad, and you advertise to the vegetarians in S. So globally, you're advertising to 5% of the general population and 5% of the protected group. But of course, you're advertising to the wrong people in the protected group. The vegetarians are not going to show up at the steakhouse. So we satisfied a very strong parity constraint, but it's totally meaningless, right? And I think this is the kind of example that tells you as a cryptographer, hopefully, that this is a field that's worth looking into in terms of what are the actual, how would you define what fairness means, or how would you circumvent this kind of adversarial steakhouse behavior? Okay, so my point is, fairness relies really on identifying what the relevant subgroup is, the carnivores in S. And this might be a silly example, but there's actually a very entrenched practice in the hiring world of interviewing minority candidates, but interviewing the wrong ones, the ones that are not, you say, okay, I interviewed minority candidates, but they weren't good enough. But there's some sort of a selection bias going on, whether maliciously or not maliciously, where you're not interviewing the right people from the protected group. Okay, so the perspective we're taking, which, as we'll see in a minute, is very much in line with what I told you about outcome indistinguishability before, is to talk about multi-group fairness. We are not going to specify just one protected group and try to equalize things in aggregate for that group, but rather we're going to try to give protections to a huge, maybe an exponential collection of intersecting groups. Maybe every group that can be identified efficiently from the data is going to have some level of protection. Yeah, this brings us to the notion of multi-calibration, which is actually where my work on prediction, fairness in predictions and meaningfulness in predictions started. This is a precursor to outcome indistinguishability, where the requirement was we want to have calibration not just for the general population and not just for the protected group S as a whole, right? Maybe it's a group of loan applicants and we're just going to stick them all with a probability of 0.7 in repaying the loan, and then we're not really identifying who the qualified loan applicants are. But rather, we're going to try to ensure calibration for every subset that can be identified efficiently within some computational bounds, say by circuits of a certain size, by conjunctions, by a decision tree, by a decision list, etc. Okay? So now I have a potentially exponential collection of intersecting groups, and for every single group in that collection that's large enough, if the group just has one person or has tiny mass, we're not going to be able to do anything because we don't see enough people. So we need the group to be large enough under the distribution. And then for any such group, the guarantee is that restricting our attention to that group, looking at the people within the group for whom we predicted, say, 0.7, 70% of them should have an outcome of 1. Okay, so that's a strong guarantee, and in fact, it is equivalent. I'll talk about that later. It is not too much later, but a little bit later. It is equivalent to outcome indistinguishability if you set things up right. I want to tell you about an even stronger type of guarantee that we can give and demonstrate how we achieve it through outcome indistinguishability. So this is known as multi-group loss minimization, initially proposed in a work by Blum and Likunis. And I'll tell you about results from a work of mine with Gal Yona. So now we're going to guarantee that for every group in our exponential collection, C, the loss that they experience, so the loss experienced by members of that group, it's important that I'm taking the expectation only over members of the group, the loss that they experience is competitive with the best hypothesis for that group in a class. So the predictions being supplied for that group are, as good as the best decision tree would be, the best decision tree for that group would be, or the best neural net of a certain size for that group would be. So a very strong guarantee. Okay, we're getting competitive loss for all of the groups simultaneously. And you might wonder whether this is, and a good loss to think of is the squared loss, which I talked about earlier. So it might look too strong, right? There are these different groups, and maybe one, I don't know. Can you really be competitive? Maybe group one has one hypothesis that they like, and group two has another hypothesis that's good for them. And how can you be competitive with both of these at the same time? And for which loss functions is it possible? Is it possible for the squared loss that I showed you? What about more complicated loss functions? And what I want to tell you is that it's in fact possible to achieve this. It's impossible for a really rich and interesting class of loss functions. So in particular, loss functions that are in line with what's being shown by the data. So a loss is called a proper loss. This is terminology from machine learning literature. If the thing that minimizes the loss, if giving the correct probabilities always minimizes the loss, that's a proper loss. Okay, so there are losses that are not proper, where you don't want to be predicting the correct probabilities, but this is a very natural class of loss functions, in particular losses that are in line with predictions. The predictions that will minimize the loss are in line with the true probabilities. Okay, so the loss of P star will be smaller than the loss of any other predictor, any other hypothesis H. Okay, and you can extend this, you can talk about, let's think about proper losses for now. So the theorem that we show is that you can get a predictor that minimizes the loss for all of the groups simultaneously, and you get it through a reduction to outcome indistinguishability. The result just follows from this theorem. It says that for any proper loss function that you want, for any collection of groups, exponential overlapping groups, and for any benchmark class that you care about, there exists a collection of distinguishers, so that's the reduction, so that if a predictor is outcome indistinguishable for this collection, then it is also competitive with H for all of the groups simultaneously. I'm lying a little bit. You need to do some tweaking to the predictor to make it competitive, but as far as we're concerned, this is the result. And in the 5 minutes, less than 5 minutes, I want to tell you something about this connection, because I think it's a really nice demonstration of why thinking about indistinguishable predictions gives you a lot of power to get other guarantees. Okay, so I just want to do a warm-up where we're thinking about a single benchmark hypothesis. Okay, so we want to have less loss than this fixed hypothesis H for the general population, not for groups. So I just want to show that if you want to have competitive loss with a fixed hypothesis, there is a distinguisher. We can build a distinguisher such that if you're indistinguishable for this single distinguisher, then you will also have better loss or no worse loss than this hypothesis H. And the theorem follows by just having a distinguisher for each of the hypotheses in the benchmark class and for each group, and we don't need to get into it in the talk today. So how does this distinguisher work? It's a distinguisher, so it gets an X, a predicted probability for X, and an outcome. Maybe the outcome is drawn according to P tilde, maybe it's drawn according to P star. We don't know yet. And the way this distinguisher works is it's going to output 1 with probability that's proportional to the difference between the loss that we would get for the outcome Y according to the prediction P tilde and the loss we would get if we used H, right? This distinguisher has H in its belly. We want to say that if you are indistinguishable to this distinguisher, which depends on H, it has H in its belly, then you also have competitive loss. P tilde is indistinguishable, then P tilde has competitive loss. Okay, so the important thing is this distinguisher outputs 1 with high probability if H is better than P tilde, for this particular distribution of y's, and an output 0 with higher probability if p tilde is better than h for this particular distribution of y's. And we build it in such a way so that if it outputs 1 with probability less than a half, the probability is taken over the distribution over x and p tilde of x and y, if and only if the loss of p tilde when the outcomes are drawn by y over there's an expectation here over the distribution, but I'm trying to make the notation simple. So the loss of p tilde when the outcomes are drawn according to y is less than the loss of h according to y. So if p tilde is better than h, you'll output 0 most of the time. If p tilde is worse than h, you'll output 1 most of the time. Okay. So let's look at what this distinguisher does when we give it outcomes sampled according to p tilde. So we give it y tilde outcomes. Well, now we know it's a proper loss. So p tilde is actually giving us perfect predictions for the outcomes that we're seeing. And the loss is a proper loss. So by definition, we're always going to get less loss. P tilde has less loss than h. And this distinguisher outputs 1 with probability less than a half. Okay. Well, what happens when we feed in true y stars drawn from the true distribution? If p tilde is indistinguishable, then the probability of the distinguisher outputting 1 is about the same, approximately the same. So roughly, it will still output 1 with probability less than a half. But what does that mean? We said that this distinguisher outputs 1 with probability less than a half, if and only if p tilde has less loss than h on this distribution. So now we know that p tilde has less loss on the true distribution than this h, and we're done. It was too fast to follow. There's a painfully detailed write-up in the proceedings. Okay, so that was our warm-up, and we get from that our theorem where we can actually minimize loss for all of these subgroups simultaneously for a very rich collection of loss functions. Okay. Good. So this work is leading to an emerging, I guess we call it an atlas or maybe a fairness zoo of different notions, different guarantees for predictions. We talked a lot about outcome indistinguishability, where the predictor can't be refuted. We talked less about multi-calibration, but I told you that these two notions are actually equivalent in a very strong sense. And we saw now a reduction from loss minimization to outcome indistinguishability, right? I want loss minimization. I can define an appropriate class of distinguishers such that outcome indistinguishability will give me multi-group loss minimization. So we have these nice connections, and this picture is out of date. By now we have a couple of more notions and very interesting interactions between them. In terms of frontiers, for lack of time, I won't talk about omni-predictors, but they're great. I do want to end by talking about corrective transformations. So everything we saw today, outcome indistinguishability, loss minimization, calibration, everything is geared towards accuracy with respect to the underlying data distribution. Okay? So these notions are all, as we say, descriptive. They're trying to describe the reality. They're not trying to correct it. They're not trying to aspire to some better reality. They are just trying to reflect the reality in a way that is meaningful, that, is considerate of all the different groups we might have, that is not leaving anyone out, but we're not trying to fix or change anything. Of course, it's very natural, and it's done all the time, to try to apply corrective transformations. If you have some sort of affirmative action policy, some corrective discrimination policy to get to a better world. And this raises interesting questions once you think about it from the perspective that I told you about today. Really, if we can agree on suppose we can agree on how we would want to correct the world. Okay, there's some corrective transformation, tau, that we would like to apply to P star, and that would fix problems with discrimination in the data and, the historical issues that are present in the data, that we want to remove or improve on. But we don't know tau of P star, so, we don't know P star, so we can't get tau, we can't transform P star. All we can get are these approximations. And so if we apply this corrective transformation to something that is not really P star, what is going to happen? So it's natural to try to be indistinguishable, and it isn't always possible. So try to get to a new predictor that is indistinguishable from tau of P star, from the way we would want to correct the true reality. And we have, this is work with Cynthia Dwork and Omer Reingold, where we characterize the transformations for which that's possible. Okay, so I want to wrap up. I think no one needs to be convinced anymore that algorithmic predictions are incredibly impactful for individuals, but they're just numbers, and we need to make sure that they are meaningful and that they are fair. So we have these new perspectives, outcome indistinguishability and multi-group fairness, that are very computational and cryptographic in nature, and I think are very promising or interesting to work on. The guarantees are in line with accuracy, and we have by now a rich theory. I didn't tell you about implementations and deployment, but I've been involved in using some of these ideas in the context of medical risk prediction in Israel. They work well in practice, or they seem to work well in practice. So I think it's a very interesting story and very promising field to work on, but there's a lot more to be done. And I think the main thing is, really working on biased data distribution. So what can we say? If the data themselves, we know the data are not fair, right? The data are coming from the real world where there's terrible discrimination going on. So what can we say about that? I think there are also very interesting questions that you're welcome to ask me about in a minute or during the coffee break about fairness in other settings. Prediction is not everything in algorithms. So in complex resource allocation problems, I'm particularly interested in two-sided matching markets. So you can ask me about that. And I think I'll end here. Thank you.
Thank you very much. Thank you very much, Guy. We have time for questions. If you have any questions, please step up to the microphones.
Okay, so thanks for the very inspirational talk, and obviously I have lots of questions. I try to ask the best of them. I can't promise. So it kind of has two aspects of question. So I think you mentioned that the loss depends on kind of the availability of features and kind of how much data you have about people, basically. So it depends also on the privacy invasiveness of the operation, right? So if you're very privacy invasive, you know everything about the person, probably you can know what they're going to do better than they know it themselves. I mean, that's kind of, it's a thesis that people have posted, and it might be true. Then the question is, do we want that? Like, so how do we want our predictions actually to be too good? So that's one question, but that's only the passive security part of it. So the active security part is that you can make, like, the best predictions are those that you caused yourself. So in a way, you can get a perfect predictor if you kind of do an active attack and you make sure that the outcome is exactly what you want. So kind of, can this kind of self-fulfilling predictions also be kind of modeled in that model? So it's kind of two questions wrapped into one, but maybe there's some connections.
Yeah, let me take them one by one. So I think the first question is wonderful motivation for many talks that I hope we'll hear in Eurocrypt about, how to get the best of both worlds. Do machine learning that is able to be informed by very granular data about individuals while still preserving privacy. And we know that we have amazing work and techniques on that. It doesn't have to be an either or choice, right? Maybe we collect data, but everything is encrypted and is being run using secure multi-party computation, and the outcomes are all differentially private, and we get incredible predictors with no privacy harms, right? Like, I think that's the world that we should sort of be inspired to move towards. For the second part, it's interesting. I'm going to take the question in a different direction than I think you asked, because I don't think necessarily, of the predictor as, you're thinking about a game where the predictor is being rewarded if the predictions are perfect and the predictor is trying to cheat. It's interesting. I haven't thought about it, but I'm going to take it in a different direction, which is, the individuals are trying to win, right? So it's kind of, gosh, I forget now, but there's this sort of a rule or whatever that as soon as you publish your decision-making rule, people are going to start gaming it. If someone remembers, this is a principle, but I forget the name of it. So for example, like if your predictor says that people who, maybe you find some causal relationship, some correlation in the data showing that people who have many books in their home do well in college. Okay, so you use that for your college admission. I mean, the next thing that's going to happen is that next year people are going to start buying books and having them in their house. So this is known as setting a performative prediction, and there's a lot of beautiful works on it, particularly some work by Moritz Hart and his group that I recommend looking at that I think is interesting, and it's the kind of thing. Yeah, I like that you brought it up because, again, it's a kind of, there is a type of adversarial thinking involved that I think is very relevant for this audience. So something else to look at.
Thank you. More questions?
Yes, I'll ask a quick question then. So for the OI condition, it seems to me again like it's sort of a sanity check, if that's fair to say, for a predictor. We would like it to satisfy this notion of OI and ideally the strongest notion of code-based OI. So do you think there are sort of techniques or cryptographic techniques to say distinguish between, say, two predictors that satisfy this code-based OI condition? How should I decide which one to use?
It's a wonderful question. It's a question that's there's old work on it and there's new work on it. And there's good news. So if you give me two different predictors that are, so there can be, the motivation behind the question is that there can be many different predictors that satisfy, that are all that are indistinguishable. And suppose we are presented with two of them. Okay, we're presented with two predictors and they're both indistinguishable to our set of distinguishers that we have determined. So which one should we use? So you don't have to choose. There's actually a simple procedure for refining them that will get you something that is better than, if they're different in both OI, it will get you something that is at least as good as the best of them and hopefully better than both of them. And it's an efficient refining procedure. It will still be indistinguishable. And kind of the issue is the minute these two predictors are both indistinguishable but different from each other, the predictors themselves, if you look inside them, they're telling you how to distinguish between them, because you can look, let's look at the people for whom predictor 1 said 0.3 and predictor 2 said 0.7. Let's draw some sample examples and see what the actual outcome is, and now we can refine both predictors very easily. So in general, with outcome indistinguishability, there's this really nice feature that I only talked about briefly or hinted at, that any refutation, anything you find that shows you're doing something wrong is a bummer because someone refuted your predictor, but it's also a path towards progress. You can refine your predictor and do better.
Okay, so thank you very much. We will take a break now. Let's thank Guy again.
Thank you. יופי.